Hello everybody, my name is James Mattard, and the topic for my presentation today is how increased sea ice melting affects ocean currents. Ocean currents are influenced by a number of factors including wind, tides, the Coriolis effect, and density differences. We're going to focus on how density differences impact ocean currents. The two major factors affecting the density of ocean water are salinity, or the amount of salt content, and temperature. Cold water is denser than warmer water, and water having a higher salt content is denser than fresh water. Therefore, warm, less salty water moves towards the surface. Cold water, higher in salt content, descends below to lower depths, thus resulting in the formation of ocean currents circulating throughout the globe. The global ocean conveyor, also known as thermohaline circulation, is, as I just mentioned, the normal route that seawater circulates throughout our ocean systems, bringing unique climates to all regions of our planet. In the name thermohaline, the thermo refers to temperature, while haline refers to salinity of the water, because, as I discussed in the previous slide, these two factors are the reason ocean currents exist. In the global ocean conveyor, the red represents warmer water closer to the surface, the blue represents colder water that is deeper, and the purple represents the absolute deepest ocean currents. Here you can see the Gulf Stream, which some of you may have heard of before. It's warm water going up the Florida coast, up to the Carolinas, then shooting over to northern Europe. This whole region here, this part of the global ocean conveyor, is referred to as the Atlantic Meridional Overturning Circulation. Throughout the rest of the presentation, I'm going to refer to that as the Atlantic MOC. Here is a more detailed view of the Atlantic MOC, which is vital to the Northern European climate. Unfortunately, ice melting in the Arctic and Antarctic is occurring at a higher rate due to climate change, bringing more fresh water into the oceans and gradually disturbing the salt level differences necessary for these currents. There is a delicate balance between the amount of fresh water normally melting from ice caps and the natural salinity level of the ocean. But if we disrupt this too much, the climates around the world will significantly change. The Atlantic MOC, if it becomes ineffective and fails to bring these warm ocean currents from the Gulf Stream to northern Europe, the temperatures there could drop as much as 5 to 10 degrees Celsius, which is 9 to 18 degrees Fahrenheit, on average over the course of a year. This is a huge amount. If you were outside and the temperature all of a sudden drops somewhere in that range, let's say 12 degrees Fahrenheit, you would definitely notice the difference. An interesting fact, it will take approximately 100 years for a particle of water to travel one full cycle of this global ocean conveyor. Just lets you know how vast these ocean currents are. Is there feedback from sea ice melting? The answer is yes. We learned from our reading this week that albedo is the amount of solar energy reflected by features of the Earth's surface back into the atmosphere. Pure, clean snow has an albedo of approximately 85%, a really high number, and sea ice has a similar amount. Therefore, when more sea ice melts, it is exposing more of the ocean, which has considerably less albedo and in turn absorbs a lot more solar energy. The increase in solar energy results in warmer ocean temperatures and eventually warmer land temperatures due to the global conveyor belt, as we learned earlier. This results in turn in even more sea ice melting because now the temperature throughout the world is increasing. So evidently there is feedback because as sea ice melts, it exponentially increases the amount of sea ice that will melt in the near future because of its high reflectivity properties, or albedo. Regarding timescale, it is natural for some sea ice to melt into the ocean, but the amount of melting is only increasing and is affecting our vital ocean currents. Researchers are installing underwater instruments that measure the flow and speed of these ocean currents, and there is evidence that both of these parameters are steadily decreasing. Since 2004, experts say the Atlantic MOC current has decreased by 30%. One of the latest assessments by the Intergovernmental Panel on Climate Change determined that the Atlantic MOC will most likely slacken to an ineffective level by the end of this century. Experts predict that flow by that period will be approximately 54% of its full strength. However, there is good news. If we can limit human contribution to climate change, the ocean currents will return to full capacity. Researchers have discovered that during the last glaciation period, which occurred approximately 100,000 to 10,000 years ago, the Atlantic MOC during that period reduced to 50% of its strength. But we see now that it did eventually return to its normal state. The Earth can heal itself if we can help stop these changes in a reasonable amount of time. I hope you all enjoyed my presentation and learned something about how sea ice melting is affecting ocean currents and will have devastating impacts on our planet if the current trend continues. Thank you for listening to my presentation, and I hope you have a great day.